a way to measure pH. Yeah? We have another way, an acid base or a pH probe. This is a pH probe. It measures pH electronically.
How was magic?
There is, I'll explain it here as I go through the process. In order to use a pH probe, we need to calibrate it. The pH probe is stored in a bottle of solution. It needs to be kept in a solution constantly. It has a cap that has a seal in it. A pH probe has a glass bulb at the end that's made of very thin glass, and ions can migrate through the glass, and it changes the voltage that this probe produces. In order to calibrate it, I can put it in solutions of different pH. This is a solution that maintains a constant pH. It's called a buffer solution. New term. Put it in your notes. B-U-F-F-E-R. A buffer solution maintains a constant pH. We will talk about why they do that, how they do that in chapter 18.
Chapter 18 can be really hard, isn't it?
Yeah. All the chapters are hard. Why did you have an easy one?
The first one.
This is a buffer solution that is made to maintain a constant pH of 4. This one, 10. So what I do is I put the probe in this solution. It's already very close, but I go to the calibrate portion of the program, and I tell it pH of 4, and right here is the voltage that the probe is producing at a pH of 4. So I tell the computer this is a pH of 4, and this is the voltage that a pH of 4 produces. And then I rinse it off and put it in this solution. This is a buffer solution that maintains a pH of, can you guess? 10. I've already been through this calibration procedure, that's why it's so close. But I tell the computer that's a pH of 10, and that's the voltage that the probe produces when it's in a solution of pH of 10. And by doing that, for instance, I have a buffer solution that has a pH of 7, or pretty close to 7. And again, what's a buffer solution designed to do? Maintain a constant pH.
Can you just use deionized water?
Because carbon dioxide will dissolve in and out of the air. And it makes, so water exposed to the air, its pH starts to drop down. And that's not bad, considering the calibration process. Okay? So we have pH probes that we use to measure pH as well. And we're going to use the pH probe to do the lab that I'm going to demonstrate.
What's the pH of the air? Or is there none?
Solutions have pHs. Typically aqueous solutions have pHs. Caps back on these so I don't spill them again. Now, an acidic solution and a basic solution, if I add them together, they neutralize each other, don't they? Right?
Yeah.
If I add a solution that contains hydronium ions with one that contains hydroxide ions, and I got a reaction like this. What's it made? Water. It's the opposite of the reaction that occurs in water, where water molecules exchange hydrogen ions and become hydroniums and hydroxides, right? This is called a neutralization reaction, where hydronium ions and hydroxide ions mix together. And what I'm going to do is I'm going to take a beaker. I'm going to put a HCl solution in the beaker that has a low pH. And then I'm going to add a sodium hydroxide solution to it. And the goal of doing that, which is something called an acid-base titration, that's the new word. The goal of doing that is, if I take a solution, for instance, whose hydroxide concentration I know, and I add it to a solution whose hydronium ion concentration I don't know. If I add this solution to this one until the pH is 7, won't I have added the same number of hydroxide ions as I had hydronium ions in the acid solution to begin with? If I know the volume and molarity of the solution that I add to the acid solution to neutralize it, that'll tell me how many hydroxides I added. That must be the amount of hydroniums that were in that acid solution to begin with. So I have been able to quantitatively determine the concentration of an unknown hydronium ion solution. And we could do it the other way around as well.
So what's the definition for titration?
So now, definition's a little broader. I won't be asking you for a definition of that because we use titration in many different kinds of chemical situations. But it's a quantitative procedure that don't write it down because I'm not going to be asking you the definition. We're going to be using a titration to accomplish a purpose, right? But a titration is where you add one solution to another to be able to determine quantitatively what the concentration of the unknown solution is. We're going to do two of them. One in the week we come back from break, where we're going to take an unknown acid solution or base solution, I forget which, and a known the other, and figure out what the unknown one is. And then hopefully, if we have time, the week before finals, we're going to do an oxidation reduction version of the titration. Same idea. Now, I'm going to demonstrate to you why the acid-base titration is so good at doing what it does. So good at determining the unknown concentration.
This is the lab we were going to do
There have been years past when I've had you do this experiment. Now, I need to do something a little different here. I need another. We're going to graph the pH changes as I add the sodium hydroxide. I'm going to use experiment 23 for this. But I need to go back to the calibration procedure. I'm going to do that real quick. I need to recalibrate because the calibration settings are different for the two different programs. I'm going to add some hydrochloric acid to this solution. What's going to happen to the pH?
Down.
It's going to go down. Did it go down? Oh, actually, the pH is right here. You can't really see it. 2.25, about 2.25. Okay, then I'm going to use something called a burette to measure the sodium hydroxide solution. Now, today, all I'm going to use it for is a way to drip the solution in one drop at a time. But we're going to use a burette the week we come back to be able to accurately measure volumes of solution that are delivered from this valve. We can read the scale on this. It's probably too far away for most of you to see. We can read the scale on this accurate to the nearest 0.02 milliliters. That gives us about 4 significant figures in measuring a volume of solution from this. Typical volume, it'll hold as much as 50 milliliters. Typical volume we use is 20 or 25 milliliters. And it will give it 25 milliliters to the nearest 0.02 milliliters. That's better than 1 part in 1,000. When we do our titration, all right, that's already a problem. Work. I'm going to fill a burette with the sodium hydroxide solution. The burette has a stopcock at the bottom. Works like our gas valves. When the handle is perpendicular, it's off. When it's parallel, it's on. And when I add the sodium hydroxide solution, what do we expect to happen to the pH?
Go up.
It'll go up. The question is, how is it going to change? Right now, the pH is right about here. When we're done, the pH will end up around 12. The question is, what is the shape of the graph going to look like? Okay, I'll give you a little hint. pH is a logarithmic measure, isn't it? Right? Okay, so I'm going to get this started. Let's make sure I'm ready to go.
Oh, so it's gonna go.
Collecting data.
No, it's gonna go.
We go slow, we go fast, and it's gonna be accurate. That's what I said. That's what I said. I know what that means.
I didn't have time to test this ahead of time, so, we'll see what happens. pH is going up, yes? The amount of sodium hydroxide I have to add to get the pH to go from 2 to 3 is a lot more than the amount of hydroxide I have to add to get the pH to go from 6 to 7, right?